All right, welcome ladies and gentlemen. This is the detailed video of the ZeroG-200, our entry into Mauser's ISS design challenge. And so I already have a quick intro video to this product. So if you want to see the 90-second sort of commercial style video, go ahead and check out that under my videos and you will see that, and I'll link that description below. But this video is meant to be more of a detailed video, sort of get into the nuts and bolts of this whole thing. So this one's going to be a little bit longer, and yeah, so let's go ahead and take a look at this. So if you didn't watch my intro video, this is again the entry into Mauser's ISS Design Challenge 2016. This is what we're calling the ZeroG-200. So astronauts aboard the International Space Station spend most of their time in orbit performing one of two activities: science or having fun. Hi, my name is Andrew Denio. A couple friends and I accepted the challenge. We spent a lot of time thinking about what innovation could be 3D printed, also contain electronics, but most importantly was important to astronauts and very useful. So our project is the ZeroG-200. Its primary purpose is to provide three-dimensional acceleration and gyroscopic movement data for analysis to improve cardiovascular and strength exercise in a microgravity environment. Or put simply, it's a fitness tracker in space. An astronaut's health and exercise are extremely important. After spending long periods of time in orbit, human bone and muscle density tend to degrade because one very important factor is missing: gravity. To counter this degradation, astronauts spend 2.5 hours exercising almost every day. The exercise routines are closely monitored by physicians on the ground, and improvements can be made based on feedback from the astronauts, as well as biometric data from heart rate sensors worn during that time. The ZeroG-200 provides additional feedback for these exercise routines. Worn by the astronaut during a routine, it captures 6 degrees of freedom. The acceleration and rotation information logged by the ZeroG-200 can be analyzed either by astronauts on board the ISS or back home by physicians. This analysis will further improve exercise routines and provide feedback on how humans move in microgravity environments. Right now, the unit can capture and log movements up to 700 times per second. There is even a built-in step counter, so while the astronaut is on the treadmill, the ZeroG-200 will count and display the number of steps during the routine. So what makes this all possible? Inside you'll find the Arduino 101, a microcontroller powered by Intel's Curie microprocessor, and contains a triple-axis accelerometer and gyroscope. Additional components include a micro SD card module, real-time clock, vibration motor, RGB LED, tactile buttons, and an OLED display. The hardware and software, they're open source. So what does this mean? Well, first it means that someone else who comes across our ZeroG-200, if they like it, they can make one for themselves. All they have to do is purchase the components, 3D print the enclosure, and upload our original code or modify it for their needs. But what I'm really excited about is the idea of astronauts tinkering around with our open code. Even though the ZeroG-200 is primarily a fitness tracker, it is capable of so much more. It is powered by Intel, so it allows for very fast processing in a compact form. Okay, so that's a little spill, right? So let's just go ahead and get into sort of like the nuts and bolts. Okay, so again, this thing is primarily a fitness tracker, but it is capable of much more. Right now, the unit is sort of big, as you can see. You know, my hand here. This is about to fit in the size of your hand. So it's meant to be worn by astronauts, but this is just a prototype. It can definitely be scaled down to be something a lot smaller. So first, let's take a look at what's inside. Okay, so here's the inside. As you can see here, there's a what we call like a shield. This red thing right here, battery, LED, and then so if you take the shield off, you'll find the Arduino 101. So if you don't know Arduino, it's a microcontroller that allows for sort of easy programming and is mainly used in prototype applications. The 101 is powered by Intel, as you can see here. So it has the Curie microprocessor, which is right there, and it contains a triple-axis accelerometer and gyroscope. So it allows for what we call 6 degrees of freedom. So you get 3 from the accelerometer, 3 from the gyroscope, and it can basically tell you how this thing is being moved in space. So acceleration is movement in one direction, and the gyroscope is rotation. And they each measure along the X, Y, and Z axis. And on our enclosure, we have which direction X, Y, and Z are relative to this unit. So X is that way, up and down, Y is left and right, and Z is up and down. All right, so we have access to the USB port, as you can see here, because you can program and access the micro SD card from there. And that's basically your serial port to your computer. And we don't have the power module accessible. However, if you wanted to modify the STL file, which is our 3D enclosure file, you could do so. We have a little section for our 9-volt battery, as you can see here. So this thing does take quite an amount of voltage in order to sort of be powered, because of the Arduino 101 itself. Its operating voltage, input voltage is between 7 and 12 volts. So we're using a 9-volt battery. But the sort of meat of our project is all on this, what we call shield. So this is like an Arduino shield. Now, of course, the Intel Arduino controller is the computer, but these are all our sort of peripherals or accessories. So let's take a look at the bottom first. As you can see here, we have a micro SD card module. So we have our SD card plugged into there, and that when this thing sets inside, it's actually, if you wanted to, you could open up a hole right here as well and access the SD card. It sort of lives right in between the barrel plug for power and the USB port. But we have our micro SD card module. If you can kind of see those letters right there, it's connected to the SPI bus on the Arduino. So it uses the SPI communication. The other module you can see down here, besides a bunch of these wires, is this CR2032 Energizer battery and holder. So you might wonder what that's for, even though we have a 9-volt. So we'll go ahead and flip this over. That battery is tied directly to this module right here. So this module right here is called our real-time clock. The module that we're using is called the Tiny RTC, and it's using an I2C interface, as you can see right there. So unlike the SPI bus, it uses I2C. So what is a real-time clock? A real-time clock allows for you to keep the time on something even when it's powered off. So that's why there's a separate battery. And this is actually the same sort of technology, low kind of technology that's in your computer at home, on your desktop. So when you turn your desktop off and you turn it back on, you might wonder how it keeps the time, even though there's no power. Well, there's actually a tiny little battery inside, just like this, and it keeps the time. And you can actually, instead of a CR2032, you can use I think it's called a LR2032 or 2032, and it actually recharges while it's connected to power. I just don't have one of those at the moment, so a CR2032 will work. So this is a little clock, and also what we got up here, this is a vibration motor. It's called a coin cell sized vibration motor. As you can kind of see, it kind of looks like that battery sort of thing, but it's kind of the same sort of vibration motor that's in your cell phone. So if you just turn that on, it'll vibrate. So we actually have that connected to a transistor right here. So you can see that transistor. It's kind of hard to tell all these connections right here, but the positive lead is connected to 3.3 volts, which we get off of this bus that's underneath here. And the negative lead is actually tied to one end of the transistor, and we use one of the pins on the Arduino. When we set it high, that other side of the transistor, this is an NPN transistor, the emitter is connected, the emitter and collector are both connected to either the negative lead of the vibration motor or ground. So when we set that high, it vibrates the motor. There's a reset button right here that just kind of came with our shield. Again, all these components are listed in our files on GitHub, so go ahead and check those out so you can see exactly what we used. So this was included with the prototype shield. We have two buttons here. These are basically selector buttons. They're almost the same thing as this, just the buttons are slightly higher, raised out of their platform. And we have an OLED display. So this is the I2C OLED display. Its resolution is 128 by 64 pixels. And if you can see this little line right here, everything above that line is going to be in yellow. Everything below it's going to be blue, bright blue. We have an off-on switch right here, and that's just kind of soldered into the breadboard. And then we have an RGB LED right here. So if you've never seen an RGB LED, what that is it's one LED, but there's 3 tiny little emitters in there. And there's one for red, one for green, one for blue. So you can light up all 3 either individually or one at a time, or make a mixture and that sort of thing. And then basically all that's left is wires connecting everything. So you have 4 wires for your RGB LED. You have some wires for your OLED display, and that's I2C as well. So these are both on the I2C bus. You have your micro SD card, which is on your SPI bus. So this schematic is available on our GitHub. You'll be able to see how we wired everything. I included both a version where you can just build it on a breadboard, like a normal breadboard, or you can look at our files to see how we wired everything here. It's pretty simple. Just bunch of wires in the back. But again, this is a prototype, so this definitely could be used in space. And if the astronauts like it, it could be scaled down to not be in such a sort of big form. You could get it more compact and build your own printed circuit board to contain only the necessary components, as well as not have all these wires sort of running around. All right, now let's talk about the 3D printed enclosure. So those are all the electronics. 3D printed enclosure was printed by my friend Kevin Johnson. And basically what we have here is, if you can see sort of where these screws are, the screws are being held down, or holding down the Arduino. So underneath the Arduino is basically just some spacers, and those are screwed into them. And then we have our compartment for our 9-volt battery. We have these little tabs here on the side, and you'll see how those lock into the top, the hole for the USB, and then on the back we have our logo for the ZeroG-200. Let's take a look at the top. So this is what we call the front half, and up here you can see this little hole here. That's where our RGB LED is going to be plugging into. We have our logo up here. The screen is going to be appearing through there. This is a little hole to access our switch, which was actually inspired by the Star Trek tricorder. And because it's sort of hard to print in 3D and have a hole, because you can't print over nothing or whatever. So we actually used this sort of concave pyramid inspired by the Star Trek Next Generation tricorder to get a switch there. So I was pretty happy about that. We have a hole for our reset button. And by the way, our on-off switch we actually call off and not off. So that's just a little nerd humor. We have these button pushers right here. So as you can see here, I can press these down. These are 2 separated tabs that press our buttons. And like I said before, this is our XYZ reference. If we look in the back, we can see those button pushers have a little bit of a sort of elevation to them so they can press the buttons. And everything else is just kind of keeping things in space. So this is to keep our 9-volt battery in space. This is to kind of wall off the 9-volt. And so you can take a look at that. These are the holes for the tabs right there. So that is our front half. I really like these button pushers. They work very, very nice, and they shouldn't break. They're pretty solid. They're just flexible enough so you can press the buttons beneath them. So if you look on the front half, these are those buttons that are getting pressed. Okay, so like I said, the schematic is in our files, so you can take a look at how everything's wired. But we're just going to go ahead and connect this shield. So everything on the shield is soldered except for one component. The vibration motor. There are some versions that have like a little piece of adhesive on the back and you peel that off and you stick it on here. Our first vibration motor was like that. This one, however, worked a little better and didn't come with any adhesive. So I just used a little bit of hot glue. You might be able to see that underneath. And so yeah, just a little bit of hot glue. And like I said before, you can see our SD card module is right there. So right now, when the top gets put on, you won't be able to access it, but you could totally just open up a hole right there if you wanted to do that. All right, so that's how that lives in there. And then we have our top. So the RGB LED is going to go in that little hole. So when this were to be put finally together, what we'd recommend is after you sort of insert the LED into this hole, that you use a little bit of hot glue or some sort of like duct tape or something to kind of just hold that in there, because right now it's sort of meant to be removable just so I can access this a little better. But you'd want to, after you put it in there, just put a little bit of hot glue like right there. Then we basically just line up these tabs like that. And there we go. So that's the ZeroG-200. And let's take a look at it. So again, you'll see our RGB LED right there, screen, and buttons, and our off and not off switch. Okay. All right, so now let's turn on the unit, switch on. Got our Mauser, Intel, and Amphenol logos. Introducing the ZeroG-200. All right, so as you can see right here, it defaults to this time screen. And if you see some of like the, you might see a line or a flicker, that has to do with our fluorescent lights that we're using to film this. So in reality, you won't see that. This is how you kind of see it right now. All right, so defaults to time. So to basically change through menus, you're going to be pressing the 1 button, and for sort of selecting and scrolling, you're going to be pressing 2. So let's just go ahead and see how to change the time. So you'd press 2. It's going to ask you to set the hour. Let's just go ahead and, oops, I skipped the hour. So let's change the minute. Let's increase it by a year, increase the month, change the date. There you go. So as you can see, it said time set, and I'm not sure if you could hear it, but I could feel it. The vibration motor was going off, and as well as the LED, just to let you know that your changes took effect. So as you can see here, we changed the time and changed the date right here. But just to prove that I can change the hour, I'll just go ahead and do that as well. So 1 goes through the different things, and then 2 is your selector. So there we go. So so that's time. It's basically a clock and calendar. And again, if I turn this off, as you can see, it says 11/20/2017. If I turn it off, the real-time clock should be keeping that time because of that CR2032 battery. And when it boots back up, we should see that same time. So there we go. So that intro screen, you can actually sort of shorten if you want. This unit can load very fast. We just wanted to sort of display that you can make sort of bitmap images on the screen as well. So this graphics display is actually a contribution from Adafruit's graphics library. If you don't know Adafruit, go check them out. I'll link them below. They have a lot of good open hardware and software. And so to get through the different menus in your screen, you're going to be pressing the 1 button. So the next application that we have here is called raw IMU. So IMU stands for internal measurement unit, which is basically our accelerometer and gyroscope. So when you press 2, it's going to give you the values that are coming from the accelerometer and gyroscope. Let me just kind of zoom in here a little bit so you can see that. So we have our accelerometer measurements, so AX, AY, AZ. So again, that's in reference to this coordinate system right here. And then we have GX, GY, GZ, which is the same thing. So again, your accelerometer is how fast you're accelerating in this direction or this direction or this direction. And gyro is how fast you're rotating in this direction, or this direction. So those are the raw values. It might seem like the numbers are updating very quickly, and they are sort of. Those numbers are basically updating 60 times per second, which is pretty fast. But in terms of taking measurements, it's not really fast. So this is basically just a sort of prototype application to sort of give you those measurements. And so you can see them. So actually what's the reason why it's slowed down so much is the Adafruit graphics library hasn't been well sort of modified for the Arduino 101, and so it takes time to update this display. So if you turn off updating the display during these values, it'll go a lot faster, and I'll sort of get back to that in a little bit. But right now this is just sort of like a demo, and it says press 1 to stop. So we'll go ahead and press 1, and we get our vibration and LED to let us know that we stopped. Okay, our next application is what we call Tap It. So Tap It is a game, a zero-G game, or it can be a game in normal gravity. Basically what we're gonna do is we're gonna tap one side of our unit, and it's gonna tell us which side we tapped. And that's according to this XYZ. So let's press 2. Okay, so boom, -Z. So I kind of hit it from the bottom. So it lights up a different color for each axis. X, Y, and Z like that. So it's kind of a simple game, but you get the point. So we'll go ahead and stop playing. The next application is called LED Play. So this one's pretty cool. So we'll go ahead and press start. So what it says is press 2 for brightness, press 1 to continue. So if I hold down 2, you see that red LED getting brighter and brighter. So right now, again, there's RGB LEDs in there, but right now I'm only controlling the red one. This goes up to 255 in terms of brightness. So right now you can't really see it getting too much brighter, but it's getting brighter. Press 1 to go to green. So green, same thing. You can just kind of hold this down. This is, again, just sort of like an educational tool, not really meant to be like a game or anything like that. Then we have blue, sort of thing. Now the really fun part is when we come to this screen. So this one is going to let us do red, green, then blue, but when I go to green, it's going to keep the red value. So if you know, when we have our values 0 through 255, that makes 256 values. When we multiply 256 red values by 200 possible 56 green values and multiply that again by 256 possible blue values, we get a color combination of over 16 million different types of colors. And what I'm going to show you here is basically sort of the most common sort of RGB value, which will give us white. So if you give these values at like 100% of red, blue, and green, you'll get white. So I'm just going to increase red. Let's go to like 30. I'm going to go to green. Let's do 30, around 30. And then blue, we'll do around 30. So you can kind of see here that gives us like a whitish sort of like LED. If you were to like look really closer, like let's see if I can focus in. Yeah, you can't really see it too much. But the human eye can sort of see the actual like individual LEDs in there if you look up really close. So that's LED Play. Next we have Free Fall. This is sort of a fun game. So when I press 2, I'm going to hold the unit a little bit above the camera, and when I come down here, you'll see the word Free Fall light up and this light turn green. So basically it's detecting when the unit is in free fall. So if I just drop it, it'll be in free fall and it'll detect that. So let me go ahead and start it. See, like that, and it went away. So as you can see here right now, this light isn't lighting up, only when it free falls, like that. So what's interesting is in microgravity, you're basically in free fall the whole time, right? So you would think that this game isn't really useful in microgravity, but what might be interesting is to run it and see when you can make the light not turn on, right? So on Earth, the game is sort of to make this light turn on, but in space, it might always be on, and you might want to see if you can turn it off somehow. So we'll go ahead and stop that. The next game is called Motion. This one's kind of like Tap It, except it's going to just detect which way you're moving and display the axis on the screen, as well as light up the color in the same sort of color combinations as Tap It. So go ahead and start it. So if I move it this way, you can see that's like the Y. It's sort of doing all three at the same time. So this one's like Z's like pretty easy to see, but it's really hard to move just in one axis. And what's sort of fun about Motion is it's sort of updating all the time. So it's only doing red, green, and blue. But when I move it around, you might see like different color combinations. Like I see purple a lot, sometimes yellow. So those are like the different sort of like variations of colors you can get when you move this thing in more than one axis. So that one's pretty fun. Our next one is called Log IMU. So this is basically our fitness tracker. So remember all those values that we got from raw IMU? This thing is actually going to not display it on the screen, but log it on the SD card. And on the SD card, it's going to log all those values as well as the timestamp of when you started the program, and that is based on what we set our calendar to. And then it'll also give you the amount of milliseconds that for each different value. So right now we can get up to about 700, a little bit less than 700 sometimes values per second. So if you look at an output of this, you'll see this number starting with 0, which is 0 milliseconds, and it'll go all the way up until you stop. But if you look at like the number 1000 or the row where you get the number 1000, that'll be 1 second, and you can basically sort of count how many rows you have before that. So right now it averages about 650 times a second. So what you would do to start this is hit 2, and it says press 1 to start logging data. So you press 1 and it says logging. So if you remember, I said before, the screen, refreshing the screen severely lowers our data rate. Well, I still have the screen on, but it's not actually updating right now. It's just keeping this one thing until I press stop. So right now, if I move this thing along, it's measuring all these values. It's measuring the rotation values in each one of these axes, and it's logging the acceleration. So how you'd use this as a fitness tracker is you basically strap this to the arm or a leg or something, and then when it moves up and down or rotates, you'll get the values from there, and then you can use data analysis to interpret those values into how someone is moving. So if they're moving too fast, too slow, or just find out how people move in microgravity. So this is the program that the ZeroG-200 was built for, is this log IMU. So you would, after you're done with this, you would take your SD card out and put it into your computer and import it. Right now, the values that are being logged on there are comma separated values. So it'll give the millisecond, comma AX, comma AY, comma AZ, comma GX, comma GY, comma GZ. And at the top of that file, it will give you the date and time. And so you would import that into a program like Microsoft Excel or another spreadsheet program or a database program. and you can separate those values based on that comma and put everything in their own row and column. So you just press 1 to stop. There we go. All right, next is called AutoCal. So I'm going to set this down. See if we can zoom in, or at least focus. All right, so AutoCal is a automatic calibration of this unit. So we have our X, Y, and Z values, but sometimes those things can sort of get offset. So what I'm going to do right here is just calibrate this unit. And what this is going to do is reset all the offsets. So basically everything starts at 0. Now in the code, this thing assumes that we're on Earth. So it sort of gives an offset of 1 gravity unit for the Z axis. But if you're doing this in space, you could just make it 0 as well. So we'll press do, and what you'll see is a 5-second countdown. And what that basically is allowing the user to do is go ahead and get this thing set up before it's going to start doing the offset, because you don't want to hold it and be doing the offset because your hand can move. So you want to sit on a flat surface or like Velcro it to something and then do the calibration. And after the countdown, you'll see that it's calibrating the gyroscope, then calibrating the accelerometer, and then it'll be done. So this process doesn't take too long. And it says press 1 to start calibration. So you can see 5, 4, 3, 2, 1. Calibrating gyroscope and accelerometer, and it's done. So it actually takes way less time than that. It's just I'm updating that screen to give those values. So let's go and focus back here. All right, so next program is GyroGame. This is actually one of my favorite on this unit. So GyroGame is a zero-G game in space, meant for space. So let's go ahead and press 2. So it's asking press 2 for access, press 1 to start. So I can either choose X, Y, or Z. So you can see scrolling through there. So let's go ahead and choose Z. Z is sort of like the most one that's friendly on camera. So if I press 1, you can see how I should be rotating this thing. So it's basically wants me to rotate this way. And what this is doing is it's lighting up this LED based on how fast I rotate it. So red is actually the slowest value, but if I go a little bit faster, you can see that it's lighting up green, right? And then if I go really fast, you'll see blue. So it goes red, green, blue. And so that's me rotating it this direction. That's our Z axis. And if I press 1, it'll go ahead and stop. But let me go ahead and start again and show you like the X axis. So if I press 1, so the axis is this way, up and down this way. But to rotate about that axis, I'm actually going to go this way. So you can see me going red, then green, and blue. And then y-axis, I'll go ahead and show you that too, would be rotating this way. And so this kind of seems like a simple game, or maybe not something that's like very useful on Earth. But if you think about this thing floating around in space, on the space station, if you give it a little nudge, this thing's going to be rotating all by itself. So I can just imagine this thing, you know, being rotated in space and seeing how dead on you can get the rotation, so that it's only rotating on that axis. And yeah, it just seems like a really fun zero-G game. All right, our next application is step count. So this is sort of the other meat and potatoes of the ZeroG-200. So it's basically a step counter, so this thing's going to track steps, which might be useful for when you're on the treadmill, or what they call T2, or the Colbert on the ISS. You just press 2 to start, but then I want you to press 1 again, just so when you're ready. So basically, when it detects a step, it's going to light up this little red LED, and then it's basically going to count your steps. So there we go. Then it just says press 1 to stop. Now I don't have this necessarily logged to the SD card, but you could totally make that happen. And that is all of our demo programs. So we have 10 now. Like I said, the commands used to update the screen are derived from the Adafruit graphics library, and a lot of these programs that are in here are actually sort of courtesy of Intel. The freefall code was derived from the demo program used for the Arduino 101. Same with Motion and AutoCal. Step count was derived from there. Tappet was. So I basically, took some of their code and modified it in order to sort of be presented in this fashion. And but you'll see in the code, which I'll link below in our GitHub, that I gave credit to those who wrote the original code. So some of this I wrote myself, just depending on which program it was, and adapted it for the ZeroG-200. So that is the unit, and we hope you enjoyed this, and we see tremendous possibility happening with this thing, because right now on the space station they have biometric data like from heart rate sensors, but they don't necessarily have movement data from the astronaut. So acceleration is one of the two different ways that this unit can measure movement. And if you've been in a physics class, you'll know that acceleration is very closely related to velocity, and velocity is very closely related to position. So they're actually the derivative of one another. And so you can integrate the acceleration to get your velocity, and you can integrate velocity to get position. You'll be off by a constant, but it'll let you know. You can get a lot of data about how something is moving based on your acceleration. So we really hope that something like this will be implemented on board the ISS in probably a more compact form. Take this design and sort of scale it down, and I think you could get something really, really small. We just have these components because it's a prototype. One last thing I wanted to do is just talk about the specs that we used to make this thing. So in terms of the 3D printed enclosure, here's some of the data that we used. So it's 108 millimeters length. It is 61 millimeters wide and 34 thick. And we printed this on an ANET A8 3D printer, which is a rep wrap of the Prusa i3, using ABS filament. This is called like a silver metal filament, and using the Cura slicing software. Our layer height was 0.2 millimeters. Shell thickness was 1 millimeter. Our fill density was 25%. Our bottom and top thickness was 0.6 millimeters. Our print speed was 50 millimeters per second. Our printing temperature and bed temperature were sort of the default of what the bed wanted to, or what the printer wanted to do. And that is about 210 Celsius for the filament and about 100 degrees Celsius for the bed. There was no support type at all, and the platform adhesion type was none. Our filament diameter was 1.75 millimeters, flow was 100%, and nozzle size was 0.4 millimeters. And our team members, my name is Andrew Denio. I was the principal investigator, hardware and software developer. I did the videos, video presentation, this one, and the commercial style one, and I also did the 3D printing. Our 3D printed design was done by Kevin Johnson. He did a great job. And then we had Joe Green, Max, and Carson contribute to sort of the concept and sort of idea of this project. So I just want to give some credit to them as well. So again, we hope you enjoyed our video. We hope you enjoy the product, and can't wait to see this on the space station. Over and out.